Good morning, guys. This morning we're going to see what ratios look like mathematically. So yesterday I posted a video kind of showing visually what a ratio is and what an equivalent ratio is with scrunchies and with the drink mix. And today we're going to look at mathematically, how do we represent ratios, what are the symbols we use when representing ratios, and then how do we create equivalent ratios, like what does that look like mathematically. So let's read right here. It says a ratio is a multiplicative comparison of two quantities. That just means that to create an equivalent ratio, we're going to need multiplication or division. We can't add or subtract to create an equivalent ratio. And I'll give specific examples of that in a bit. They can be written three ways. So we have this, and this. The first one is just all words. So it says dogs to animals. The second one, it has this colon, but you still read it as two. So students to teachers. Even though it doesn't have the word to, when you read that in your brain, you should be saying students to teachers. Okay. The third way we can write ratios is as a fraction. Here's the difference. So anytime you're working with ratios that are written as a fraction, you need to look at the situation and determine, is this representing a part compared to a part or a part compared to a whole? Because the fractions that you've worked with, the ones that are just numbers up until this year, have always represented a part out of a whole. When we're dealing with ratios, which are a comparison of values, not just random numbers, okay, it's important to look at the situation, because this isn't red marbles out of total marbles, it's red marbles compared to blue marbles. So you need to look at the context to determine whether it's a part to a part or whether it's a part compared to a whole. Now, the mechanics behind, simplifying and scaling up ratios written in fractions is the same as working with normal fractions. It's just when you're problem solving with them, it's important that you determine what it is that we're comparing. So, let's look at some equivalent ratios. So it says ratios that are equivalent can be simplified to the same value or comparison. So here we have examples. 4 to 5, 8 to 10, and 12 to 15 are all equivalent ratios. They all represent the relationship of 4 for every 5. So we can check that by making sure that we can simplify these two to the same thing as 4 to 5. So 8 to 10, if we divide both those values by 2, we will get back to 4 to 5. If we look at 12 to 15, if we divide both those values by 3, we'll get back to 4 to 5. Okay? The same thing's true going the other way. You can create equivalent, you can create equivalent ratios by scaling up both numbers by the same factor. Remember, multiplying by fancy versions of 1 and such. So 1/6, 2/12, and 3/18 are all equivalent ratios because we can take 1/6, multiply by our fancy version of 1, and create these other two. We would also be able to take these and simplify back to 1/6, but I wanted to show you both directions. So multiply 1 by 2 and 6 by 2, you get 2/12. Multiply 1 by 3 and 6 by 3, you get 3 to 18. Okay, so equivalent ratios are ratios that represent that same core relationship, and you can show that they're equivalent by either simplifying down to the same relationship or scaling up from one to other relationships. And once again, yes, the numbers are different. 2 and 12 are different than 1 and 6, but this still represents 1 for every 6. We just have two groups of it. We have one for this 6, and then we have another group of 1 for 6. And altogether, that's 2 for every 12. Okay, so once again, it's not about what the actual numbers are, it's about the relationship between them. Okay, so let's look at some examples. It says create 2 equivalents that are equivalent to the ratios below. So if I take 7 to 11 and I get 2 groups of each side of this ratio, it's not what I meant to do. Now I have 2 groups of 7, which is 14, 2 groups of 11, which is 22. We still have 7 for every 11. We're good to go. We can multiply by whatever we want. I multiplied by 100. Okay, on the second one, first thing I did was do 2 groups of 18 and 2 groups of 12. Once again, it keeps the relationship constant because I have 2 groups of each of them. So I still have 18 for every 12. And then what I did, that's definitely not what I meant to do. And then since I knew that I had an equivalent ratio, instead of going back to the 18 to 12, I just went here and simplified to create an additional equivalent fraction. So I took 36 to 24 and I divided both sides into 12 groups. And I saw that 36 to 24 represents the same relationship as 3 to 2. Okay? For every 3 of something, I have 2 of something else. These represent the same relationship because if I take 12 groups of 3, I'll have 36, and then each of those 12 groups of 3 will have a group of 2 to go with because I also have 12 groups of 2. So once again, not about the actual numbers, it's about the relationship between the numbers. Okay, let's look at one that's not equivalent ratios. So this one right here, these 2 ratios are not equivalent. 12 to 4 and 6 to 3 are not equivalent because even though I can multiply 12 by something to get 6, and I can multiply 4 by something to get 3, that number is not the same. I am not keeping the relationship the same. If this is 12 for every 4 of something else and I multiply this by 2, I would also need the 2 groups of 4 to keep that relationship constant. And since I'm not doing that, it's not equivalent. On these other 2, I have 4 groups of 2 and 4 groups of 5. So I have created an equivalent fraction. I have 2.5 groups of 8 and 2.5 groups of 6, equivalent ratio. Okay, so the mechanics for creating equivalent ratios is the same as the mechanics for creating equivalent fractions. And you just need to remember that it's not about the numbers, it's about the relationship, okay? Excuse me. So let's very quickly look at, maybe a real world, not real in your world necessarily, but a situation placed in a real world situation. So Audrey and Megan are decorating for a birthday party. Audrey hangs 4 streamers in the same amount of time Megan hangs 6. If Audrey hangs 12 streamers, then how many will Megan hang? Use a tape diagram and a proportion to solve. Determine the scale factor. You don't need to know what a tape diagram is necessarily to show your work for this or to represent the situation. All they're asking you to do here is to represent the situation. So the first thing I did for this quote-unquote tape diagram, the reason it's called a tape diagram is because it looks like we've got strips of tape, is I represented what I knew. I knew that Audrey hangs 4 in the same amount of time that Megan hangs 6. So that's why I use the same size block, because they hang them in the same amount of time. I also knew that we wanted Audrey to have a total of 12 streamers. So what I did is I added groups. That's why it's a multiplicative comparison, because we can't just add single numbers. We have to add groups of a number. So I added groups of 4, and I needed a total of 3 groups of 4 to get our 12. And then since I needed 3 groups of Audrey's to get to 12, I needed to also have 3 groups of Megan's. And so what that shows us is that if Audrey hangs 12 streamers, Megan will hang 18 in the same amount of time. Because it took 3 groups of our original ratio to get Audrey to 12, so we needed 3 groups of Megan's ratio, or Megan's part of the ratio, I should say. And you can see I've written that down here. When Audrey has hung 12 streamers, Megan has hung 18. The other way she mentioned to solve it was with a proportion. So a proportion, guys, remember a proportion is just 2 equivalent fractions. We are saying that these 2 fractions are equivalent. And so if they're equivalent, we can apply those properties of equivalent fractions. If I do the same thing on the top, I do the same thing on the bottom. We can use cross products if we need to. I will post the notes of that with this, okay? And yeah, so once again, the first thing we did was represent what we knew, which was that Audrey hangs 4 streamers and Megan hangs 6 streamers in the same amount of time. On the other side of our proportion, we wanted an equivalent relationship if Audrey has hung 12. So we wanted the relationship between Audrey and Megan's streamers to stay the same, but we wanted to know what that relationship would look like if Audrey had hung 12. So once again, I need 3 groups of 4 to get to this side. So if I want that relationship to be the same, if I want an equivalent relationship, I just multiply the bottom by 3. And once again, you will see that we will get 18 streamers for Megan. Okay, guys? This is what ratios look like mathematically. I hope that you have made some connections. And let me know if you need anything.